It's now over 2 years since the Rosetta mission reached its target rendezvous, 67P. It's been an audacious mission, gaining unprecedented forensic knowledge of the comet's surface, interior structure, composition, and history.
We've noticed that there is not ice on the surface. We would be able to see that, at least not large patches of ice. You don't have skating rinks on this comet. And we also see gas in the coma. We see evidence of carbon monoxide and carbon dioxide, and the elements themselves of carbon and oxygen in different parts of the coma.
And we discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
In particular, what we have observed is that the nucleus is composed of a mixture of materials like minerals, like silicates and sulfides, which have been formed in the inner part of the solar system, close to the sun.
Because the comet is kept in a very cold environment, we don't expect it to have very high temperature phases, so it can be that this material was formed closer to the sun and was then brought to the comet later. And this for us was a surprise because we knew it for the minerals, but not so much for the organics. So it seems that the organics also can be transported over large distances in the solar system.
The most prominent, the most exciting changes on the surface, I believe it is still the big drop in the Imhotep plateau, which was 3 meters and 100 meters in height and hundreds meters in radius. But we have seen smaller scale features like a boulder, which was at least 50 meters big. It was 10 tons heavy, which, well, on the comet is just a chocolate bar of 100 grams or so, but still it's a massive thing, which has moved by 140 meters, likely due to activity, but we don't know the real reason.
It was time to decide what to do with Rosetta now its mission was complete. One option was to land it on the comet.
There were discussions about what would be the priority for the end of missions. So there were several scenarios put together, and one of the options was to do those very close flyovers. And I mean, in terms of the science objectives, that was the one that will bring us the more interesting scientific results. So it was decided by the science working team to go for this scenario. So yes, that's a very first, again, another first of Rosetta.
Rosetta's trajectory was altered to spiral into the comet, taking photos as it closed in.
Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data. So the spacecraft may end, but the science will continue. That's what we're here for. That's what this mission was for.
We just have had the loss of signal at the expected time. This is another outstanding performance from Flight Dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
One major problem faced by Rosetta and its Philae lander was low gravity. When the lander's harpoons failed to secure it to the comet, it tumbled and bounced until it was lost in the rugged terrain. But engineers love a challenge, and they have already come up with a novel answer for next time. It's called the Hedgehog.
So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake, which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we have flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly.